Hello. Right, okay, I'm just going to do some Newton's laws because people asked about Newton's laws. So let's do some of Newton's laws. This is homework for maybe like the first week of term. So it's just a good example of some Newton's laws questions, but we can do some just principles of Newton's laws to start with. So Newton has three laws. The first law basically just says, should I get the correct wording? Yeah. Basically, no force, no change. Actually, let me change that. Put a little word in there. No resultant force, no change. So, if you have something and it is either moving or it is stationary, and you have either no force or no net force, which means forces cancel out, nothing happens. And that makes sense. If you don't have a resultant force, why would you expect something to change? Why would something change if there was no forces? So, and that's what this means. Let's talk about the resultant force. So, for example, we have a person here. And maybe I shouldn't have done a person. Let's say they're being stretched because that's, what happens. And there's one person pulling them this way and another person, even longer arms, pulling them that way. And this person's pulling with 10 newtons and this one's pulling with 10 newtons. So what happens is this force and this force cancel each other out, and so therefore it's the equivalent of having no forces. And if you just had this person standing still with no forces acting upon them, what would you expect to happen? Nothing. That's fine, okay? You'd expect nothing to happen. So if you have no force, nothing happens. If you have some forces but they cancel out, these forces cancel out. If they cancel out, you also get nothing happening. So no resultant force means nothing happens, nothing changes, which is fine. And then but it becomes a bit trickier with you say, now let's have see if I can make this slightly smaller. There we go. So now our person is on a bicycle. Here they are. They're on a bicycle. Maybe it's too thin, that one. Let's go there. They're on a bicycle. And they're cycling along, and they're going along. What would you expect to happen to them? Why is that one so small? Here we go. What would you expect to happen to them? Well, if there's no net force, then there's no change. So if the person is zooming down the hill really fast, if there's no force in them, you wouldn't expect there to be any change. Maybe I need to can I select this? Rotate, yeah. Oh yeah. I'm a technical wizard. Okay, so now they're going horizontally. They're now going horizontally along though. They're going very fast. They've pedalled really fast. Their little legs have worked really hard and they're moving really fast. Now they stop pedaling. Okay? What do you expect to happen? You might think that they might slow down. And in some senses, yes, they would. But only if there is a force. If there is a force, they will only change if there's a force acting on them. So if they stop pedaling, maybe the only force that's going to act on them might be friction. But in this situation, if somebody's travelling along the road at, I don't know, nice simple, 10 meters per second, and there's no net force on them, what happens? They don't need any force to keep them going. If they're already moving, they'll keep moving. If there's no net force on them, there's no change. So they will keep moving. That's the important thing. So if there's no force, Newton's first law says if there's no net force, there is no change. So if a person's moving and there's no net force, they'll keep moving. If he's cycling along and there's no net force, he'll keep moving along. No net force means no change. Those two things are very important. In reality, if he stops cycling, there'll be friction on the road. That will slow him down, but that means there is a net force. So the questions are going to be something like, is there a net force? Yes or no? Well, let's have a look at that. Newton's second law is basically, well, if the first law says there's no net force, well, what if there is a force? And if there is a force, what happens? Well, here we have this equation. Force is equal to mass times acceleration, which basically means if you put a force on an object has mass, therefore you will get an acceleration. So if there is a net force, this equals an acceleration. And what does acceleration do? Well, come on, move. Acceleration causes either change in speed, change in direction, or if something's fixed to the floor, a change in shape. That's what shape. So let's look at our cyclist again. Should have just copied him. Let's see if I can do a better one this time. Cyclist. He's on his bike. His pedals. His body's the wrong shape. Okay, so here's our cyclist. At the start, he is not moving. Not moving at all. So, if he puts a force forward, his velocity goes from 0 meters per second up to, I don't know, 5 meters per second. That means he's got a change in speed, so therefore he is accelerating. Therefore there is a net force. If maybe, as he tries to cycle, the wind blows really hard in his face, and actually there ends up being a net force backwards, his speed might go from 5, it might go down to 4, 3, 2, 1. It might go down, means he's got another change in speed. He's decelerating, he's going slower. So a net force can cause you to change your speed, so it can change your speed up, cause you to slow down. It can also cause you to start. If you weren't moving, you then start moving. So change in speed can cause you to get faster, it can cause you to get slower, it can cause you to start moving when you weren't moving, and can even cause you to stop moving when you are moving. All of these class as a change in speed. Let's think of another example. Okay, so here we have a very badly drawn sort of pool table. And the pool balls or snooker balls are moving around. This one's moving in this direction. What's going to happen maybe when another ball ball comes in and hits it on the side. So here we have, I don't know what's happened. Somebody's hit the ball and it's travelling along, but of course you've broken. All the balls start flying around. If you have something moving in this direction, in one direction, like this, and then a force comes along the side, not in the direction of the force, like that way, and not against the force that way, but from the side, like at 90 degrees, what's going to happen? It's going to cause this to start swinging round here, which is a change in direction. We have a change in direction. So net force, F equals ma. If there is a force, and it's, so that's the F, and it acts on an m, a mass, something, therefore it means we get an acceleration, and the acceleration can just cause a change in direction. It doesn't have to cause a change in speed. See, velocity, speed. What's the difference between speed and velocity? So speed is just meters per second. Velocity is meters per second with direction. So if you change direction, you change velocity, and if you change velocity, you're accelerating. So a net force causes a change in direction as well as a change in speed or velocity. Okay, let's do the last, Newton's third law. Third law is perhaps the most easily confused, the one people get wrong the most. If object A exerts a force on object B, B exerts an equal and opposite force on A. Okay, so Newton's third law is all about two different forces. So the forces have to be the same. Let's look at the classic one is the it's like the something on a table, but people get themselves confused because you see one of the forces adding down is going to be the weight. There's another force acting up, and that is the reaction of the table. That is not Newton's third law. Newton's third law must be the same forces. So if we look at Newton's third law, the third law pairs are weight. Now what is weight? Weight is the force due to gravity acting on something. And the force of gravity, so the weight is basically the earth pulling the ball down. Okay, so if object A is earth, object B is ball. A exerts a force on object B. So earth pulling ball down. That's the first thing. So the second part says B exerts equal and opposite force on ball, on A. So B, ball, equal force pulling A, earth, but opposite, up. B, A. That's Newton's third law. Object A exerts a force on object B. A, pull, B, down, opposite direction. So the opposite must be B, ball, pulls, same force, earth, up, opposite direction. That's what Newton's third law is. So there is a gravitational attraction between the ball and the earth. The ball is pulled towards the earth due to the force, the effect of gravity. The earth is actually pulled up towards the ball. But if we remember F equals ma, This thing is the mass. So if they pull with an equal and opposite force, so this force is the same, and then we have the mass of the ball times acceleration equals the force, and then we have mass of the earth times acceleration equals the same force. Well, what you should hopefully notice is that the mass of the earth is enormous. So mass of this multiplied by the acceleration equals a force means the acceleration has to be tiny for this force to be equal. So these two values are the same. So for example, say if this was 10, yeah, the mass of the ball is, say, I don't know, 1 kilo, times the acceleration is 10. 1 times 10 is 10. Well, if we're doing, has to be, the answer for this one has to be the same, so same force, 10. But we know the mass of the earth is something silly like 6 with 27 zeros after it. I've lost count. So this number has to be so small to balance those two out to make the value 10. So if object A exerts a force on object B exerts an equal and opposite force on object A, but because they're two different sizes, it means that you don't really get any noticeable effect on one of the objects. So we can do that again. Newton's third law. Big-headed man stands on Earth, and he's very happy about it. Earth pulls man. That's Newton's down. There we go. So do the Newton's third law. Well, we just switch these two. Man pulls Earth up. Newton's third law. All we did was object A exerts a force on object B. Object B exerts an equal but opposite force on object A. The question's gone. The other thing that is pretty useful to describe Newton's third law is a rocket. Make it quite rockety. It's red. And our one-armed spaceman is flying. How can we use Newton's third law to describe what's happening to make the rocket fly? Okay, so what we need to focus on is this. These exhaust gases. Okay, so the rocket's kind of on its launch pad like this. Slightly different rocket than before. And what happens at the start? Nothing's happening. At the start, nothing's happening, and then the rocket motors kick in. A bit of colour, a bit yellow. Yeah, no, that looks like real fire. And the rocket motors kick in, and what do? Rocket pushes gases. These are the exhaust gases down. Rocket pushes gases down. So we're standing there, and you watch a YouTube video, and you see the gases kind of force, and they're pushing really hard, really fast out of the back of the rocket. The rocket's pushing the gases down. Ignition kicks inside. Lots of fuel, small spaces, clever movement with the gases, and the gases get pushed down incredibly forcefully with a lot of force, going very, very fast. Newton's third law. If this is object A, this is object B, let's rewrite it. Gases push, because it's the same force. Rocket, but it's the opposite direction, up. Newton's third law. Rockets push gas down, gas push rockets up. That's how Newton's third law works. It's the object A exerts force on object B B exerts equal and opposite force on A. Now, like the example over here, where was it? We have the Earth and the ball. The Earth pulls the ball pulls the Earth, but the ball is so light and the Earth is so heavy, you don't really notice the effect on the Earth. In this situation, it's similar. What happens is the gases are so light that the effect on the rocket is much, much less, but the gases are pushed with such an enormously huge force down that although the rocket doesn't move up as fast as the gases go down, because the rocket is much heavier, it's still enough to launch the rocket up into space. Now, when the rocket is being launched up into space, what's going to happen? You're going to have a Newton's second law. Because once it's started, once this third law kicks in, and the gas is pushed down, the rocket's pushed up, what happens is the upward force should be bigger than the downward force. Up is going to be the thrust from the engines. Down, what's down? Weight. There'll be a bit of air resistance too, whilst they're still on Earth. But as long as this is bigger than this, Newton's second law applies, and we get F equals ma, we get acceleration, and it starts to move really fast. F equals ma, starts to move really fast, starts to accelerate. As time goes on, what happens to the weight of the rocket? When you burn fuel, the weight goes down. So as this goes down, you get even more thrust, so it accelerates even faster. It goes at a higher rate of acceleration, increasing the rate as it goes along. I'm going to do the questions on a different video because there's a lot there. So, yeah, there's some questions. There's the Newton's third law. I'll stop this and then I'll do another one with the answers to the video for the questions. Okay, bye.